thank Michal and George for organizing this very nice workshop. And well, we'll start with Masaru Shibata, who got his PhD in Kyoto and many years ago, and he recently moved to Albert Einstein Institute in Potsdam. And I think, well, he's a very well known in the field. He did one of these first full neutron-star mergers, and we're happy that he'll talk about effects of viscosity in these mergers. Related back to the hydrodynamics work. So please start. Thanks.
Yeah, thank you. Yeah, so thank you very much for invitation. So I was asked to talk about the neutron-star merger and the viscous effect. So I'll briefly summarize the neutron-star mergers and the viscous effect. Okay, so first, so I'm talking about the viscous effect in astrophysics. As you know, viscosity is effect that causes the momentum transport in the fluid. And this viscous effect, or effectively viscous effect, become very important in astrophysics because in astrophysics we often handle the study the stars and accretion disk, and it can rotate differentially. For example, here, so I show the schematic picture for the accretion disk around the central object. In such case, so yeah, accretion disk has a Keplerian law, so Keplerian velocity field. So angular velocity varies like this. And in such case, angular momentum is transported from the higher angular momentum part to the, so higher angular velocity part to the lower angular velocity part. And then, so as a result of the angular momentum transport inside the disks, so fluid in the disk expand, the outer region of the fluid expand. On the other hand, the inner region of the fluid fall down to the central object. And then, so this effect derives the evolution of the accretion disk. And this is one of the most important phenomena in astrophysics. And then next, so maybe so before going ahead, so let me show the what happens in such a case. So in this example, so I consider the black holes surrounded by the accretion disk, and we performed the viscous hydrodynamics simulation in general relativity. And here black hole mass is a 3 solar mass, and disk mass is a 0.1 solar mass. And anyway, in the presence of the viscosity, outer part of the disk expand, and the inner part disk fall into the black hole. Here, so I show the density and the temperature and the entropy and the electron production, but please focus on the just the density here. Well, so due to the viscous effect, outer part of the disk gradually expand, while the inner part of matter fall into the black hole. This is a typical viscous effect. And also in the presence of viscous effect, so kinetic energy is thermalized, and then so temperature increase and entropy increase. And in this case, in the presence of viscosity in the later phase, so matter is ejected from the system. So I will not talk about the detail, but this is a typical evolution of the accretion disk, dense accretion disk surrounding the black hole. This could be the remnant of the merger of binary neutron stars. And then, so yeah, due to the viscous effect, disk expand and mass is ejected, and this matter is usually very neutron rich, and this can generate or produce nucleosynthesis, heavy nuclei via nucleosynthesis, and this can shine as an electromagnetic counterpart of the gravitational waves. All this phenomena was observed 3 years ago in the event of GW1770. Okay, so anyway, so this example shows that importance of the viscosity. But next question is that what is the source of the viscosity? And first candidate for viscosity is microscopic viscosity. So I mean that the molecular viscosity, but usually molecular viscosity doesn't play no role in astrophysics. This can be found from the very simple order of magnitude estimate. Here, so nu is a viscous coefficient, and this is written by, roughly speaking, sound velocity times mean free path. And viscous time scale is defined by the typical length scale, so R. square divided by viscous coefficient. This can be found from the dimension of the nu. And then, so for example, in the case of the neutron star, so mean free path is a nuclear, so strong interaction length scale, 10 to minus 13 centimeter. And speed, sound velocity is approximately speed of light or a fraction of the speed of light. Then substituting this value into this time scale evaluation, then so we found that the typical time scale is very large. So this is about 100 million years. So this means that in neutrons, viscous time scale by molecular viscosity is very long, and it's negligible in dynamical phenomena like a neutron star merger. So next candidate for the viscous source is that neutrinos, because neutrinos are emitted from the high temperature matter, high temperature dense matter, like merger remnant of neutron stars. And so here, so I consider the merger remnant neutron stars. And in such case, temperature of merger remnant become very high, so typically higher than the 10 MeV. And then so let's estimate the mean free path. And here sigma is a cross section of neutrinos inside the hot neutron stars. This is a well-known value, and so sigma is proportional to the energy of neutrino square. And substituting E, so the temperature of E is approximately 3 times of the temperature. And then for 10 MeV, we have this value. And then, so by a simple calculation, mean free path of the neutrinos inside neutron star is found to be about 100 centimeter for a typical value of the density of a neutron star. And then, so we found that time scale become very short. 1 second. 1 second is very short. It's approximately equal to the diffusion time in the of the neutrinos in the neutron star. However, dynamic time scale of a neutron star is much shorter, so typically 1 millisecond. And the merger remnant neutron star is also rotating very rapidly with a rotation period of 1 millisecond. Then, so this means that the viscous time scale through the neutron transfer is not negligible, but the time scale is still long, and so that means that the viscous effect would be minor for dynamical phenomena. And the third candidate is a turbulent viscosity. And in the turbulence, in the presence of turbulence, dissipation occurs at molecular scale, very small scale, but the turbulent viscosity play an effectively essential role in global scale. So I mean that nu for the viscous molecular scale become this small L multiplied sound velocity. But in the presence of turbulence, so viscous effective viscous coefficient become like this. So L, small l is replaced by the capital L. And so according to the theory of turbulence, so in the eddy is generated for many scales, and so energy transport occur from the large scale to the small scale by the nonlinear coupling of the wavelengths, wave numbers. And in such case, anyway, so effective viscosity, so in the global scale, motion of the matter in the global scale is determined by this effective viscosity. And then, so it can be, so effective viscous parameter could be very large, and then so even if the molecular viscosity is small, so in the presence of turbulence, effectively viscous parameter coefficient could be very large. And then substituting the typical value for example, accretion disk around the neutrons and black hole, then so time scale is estimated to be like this. So here, so I choose that R is the radius of neutron star, and L is just 1% of the R. So this L shows the maximum size of eddies in the turbulence. And then we found that the time scale is 0.1 second, 100 millisecond. And this is only 100 times longer than the dynamical time scale. So that means that, well, it's still long, but the effect could be more stronger than the effect by neutron transport or molecular viscosity. So molecular viscosity negligible, but turbulent viscosity could be very important. And then next question is what causes the turbulence? And so answer right now is that the fluid instability could be the source of the turbulence in astrophysics. So it's very well-known fluid instability, so which causes the turbulence is a magnetic rotational instability. This occurs whenever the magnetic fields are present and fluid is differentially rotating with decreasing angular velocity. So something like this. Here I'm showing the angular velocity as a function of the cylindrical radius, and so this is here. So angular velocity decrease with a radius. In the presence of a magnetic field and with this angular velocity profile, so we have the magnetic rotational instability. And the growth rate of magnetic rotational instability is roughly speaking proportional to the angular velocity. So it's I mean that in one orbital motion, magnetic field is amplified by exponential factor. This instability is fairly easily understood. So let's consider the disk differentially rotating, and so poloidal, so magnetic field. So this is this magnetic field line penetrates the this disk perpendicular from the perpendicular direction. And then so let's consider a slight perturbation like this. So I mean that the black is shifted inward from this line, and the green is along this line. Because in the inner region, angular velocity is higher, then so black moves faster than the green one. And also because of the presence of the magnetic field line, so between the green and blue, green and black, we have tension. Then, so anyway, so this move faster, but due to the tension, so this green so pulls this black one. Then so this black one, for this black one, angular momentum is a little bit decreased. But by the decrease of angular momentum, this black one rotates faster because it falls down, but in the inner region, angular velocity is higher. Then so it's fall down, and this go out. But this process is repeated in this process, and then so this system becomes unstable. And what is important for MRI is that this is a local instability, and so here, so I only show the one example, but there are many unstable fluid elements, and then so in the entire disk instability occurs, then so turbulence is excited. This is a well-known MRI, so first rediscovered by Balbus and Foray about 30 years ago. And since the discovery by Balbus Foray, many numerical simulations has been done in the community in the last about 25 years for accretion disk surrounding the central object. And then so now the consensus is that the viscous coefficient, so nu, so which is the same as the nu in the previous slides, is written like this. So CS is unchanged, but so L is replaced to the scale height of the disk. And alpha is some dimensionless constant with a value about 10 to minus 2, order of 10 to minus 2. So this is quite large because H could be very large. And then substituting this formula to the time scale, then so we indeed found that the time scale of the so turbulent viscous time scale become about 100 milliseconds for a typical value of the accretion disk around the central object. So then, so yeah, now, so I think that most of the astrophysicists believe that viscosity comes from turbulence in astrophysics. Not molecular viscosity and other were so neutron transport and so on and so on. Okay, so yeah, this is the first part, and from now, so I'll talk about the neutron-star merger. So first, so I'll show you some animation. So this is a typical evolution process of a neutron-star merger. Anyway, so due to the emission of gravitational wave to neutron star, so orbital separation to neutron star decrease gradually and eventually merge. And then so yeah, typically at the center, a very massive neutron star is formed. And at the same time, at the neutron star at the onset of neutron-star merger, two neutron stars collide each other with a high velocity. High velocity means that about 30% of speed of light. And then so a large amount of matter is ejected like this. And also, so because of the newly formed neutron star is highly elongated, then so gravitational torques works surrounding region, and then matter is expelled from the central region. And eventually, so if sufficient loss of angular momentum occurs, then so black hole is formed. So this black is a black hole, and then so black hole is surrounded by accretion disk. This is in a sense a typical evolution process of binary neutron-star merger. But so there are many possibilities. So this is a summary of the variety of binary neutron-star merger fate based on the numerical relativity. So this community has been performing a huge number of numerical simulations, and this is in a sense of the summary for such a bunch of the numerical simulations. So anyway, so yeah, after the merger of two neutron stars, there are, roughly speaking, broadly speaking, there are two possibilities. One is that the black hole is formed soon, and the other is that the neutron star is formed soon. So the animation I showed is that this hypermassive neutron star formation case. And black hole formation occurs when the total mass of the system is sufficiently high. And here, so threshold is just a threshold mass for the formation of black hole. By contrast, if a total mass of the system is smaller than the threshold mass, neutron star is formed. And as I showed in the previous animation, so after the formation of a hypermassive neutron star, massive neutron star, many physical process works, and then so in some cases black hole is eventually formed, and such black hole is usually surrounded by a disk. And one important discoveries findings of a numerical relativity community is that this threshold mass is typically larger than 2.8 solar mass. Of course, this depends on the equation of state, but as long as we choose equation of state for which maximum mass of a neutron star is larger than 2.1 solar mass, this threshold mass becomes larger than approximately 2.8 solar mass. And according to the galactic pulsar observation, typical mass of the neutron star is, well, we believe that typical mass of the typical total mass of the binary neutron star is between 2.5 and 2.8 solar mass. So that indicates that hypermassive neutron star formation is a typical scenario for the merger of binary neutron star. Of course, if a mass is sufficiently high, black hole is directly formed. And indeed, last year, so LIGO community found GW19425. This is the second binary neutron star merger for which total mass of the system is about 3.4 solar mass. In such case, black hole is likely to be formed soon. But according to the observation for our galaxies, binary neutron stars, so typical mass is smaller than the 3 solar mass. And then so I consider the viscous effect in this scenario. So this is the angular velocity as a function, again, as a function of the cylindrical radius. And this profile is a typical profile for angular velocity for binary neutron star merger remnant. And so here is about 10 kilometers, and in this case, outside 10 kilometers is just accretion disk. And the inside is a remnant neutron star formed after the merger of binary neutron star. And as I already talked in the first part, in the accretion disk, magneto-rotational instability is likely to occur, and then turbulence is likely to be excited, and the turbulence viscosity is generated. And then so viscous coefficient become in this form with alpha about 1%. And then so as I showed in the animation, disk is expanded and the mass is ejected, and such a ejector, nucleon synthesis are likely to occur. I think that at least in our community, this is a consensus, I think. Of course, so details we need to study detail, but so broadly speaking, this is a consensus. But on the other hand, for inside, we don't know. This is because for inside, we still have the differential rotation, but MRI doesn't occur because for the onset of the MRI, angular velocity should decrease with a radius. In this case, angular momentum increase with a radius. In such case, well, MRI doesn't occur. But anyway, so open question is that does turbulence occur in major remnant of Neutron-star? I mean that here, so turbulence occur or not. As I said, so MRI doesn't work, but still, so in Neutron-star, we have strong magnetic field. And we have a differential rotation, which is not suitable for MRI, but still have a differential rotation. And also in the Neutron-star, temperature is very high, as I said. And then in such case, convection is likely to be excited in the presence of entropy gradient. So, but unfortunately, numerical simulation for this kind of the object is extremely expensive, and now we cannot do a very accurate, physically accurate numerical simulation and a pure hint of turbulence to date for this. However, so there are several circumferential radius that which shows that turbulence may be excited. So this is a GRMG simulation performed by Kenta Kyuchi in AI Labs. So here I'm showing the density profile in the equatorial plane with a very high resolution. High resolution here means that delta X is about 18 meter and here is 17 meter. Please remember that Neutron-star radius is about 10 kilometers. So that means that the radius is covered by the more than 500 grid points. Okay, so then, so what happens in this case? So here, due to the shear motion, because the velocity is opposite, then so you can see the many vortices excited. And then so this vorticity is excited by the so-called Kelvin-Helmholtz instability at contact surface. And then in the presence of the magnetic field, in the presence of the vorticity, magnetic field is excited because due to the vortex motion, magnetic field wound up. And then so magnetic field is excited significantly. In this case, in the about 1 or 2 milliseconds, magnetic field strength is increased by a factor by 3 or 4 order of magnitude very quickly. So that means that we will have a very high magnetic field energy. And then so yeah, in the major binary neutrons, this kind of the situation is likely to be occur. Also, it's not very easy to reproduce by numerical simulation. Due to the shear motion at the mergers, a huge number of eddies are formed and the magnetic fields are quite quickly amplified. Yeah, so schematic picture is something like this. So after the merger, we have many eddies and then magnetic fields are amplified. Then so we have the further shear motion between the eddy and the turbulence is likely to occur. So this is a naive expectation, but this is circumferential evidence of that the turbulence could be excited in the merger of binary Neutron-star. Then assuming that the turbulence is excited and the turbulence viscosity is enhanced, so we consider the scenario for binary Neutron, major remnant of Neutron-star. So as I said, remnant Neutron-stars are magnetized, are differential rotating, and effective viscosity may be induced. We don't know, so might not be induced, but here I assume that is induced. Then, so yeah, we consider 3 years ago, what happens if the effective viscosity with this form is induced. And we performed a viscous hydrodynamic simulation using Israel-Stewart formalism. So simplest version of the very simplest version of the Israel-Stewart formalism. And here, so I'm showing the density in the equatorial plane. So this is the animation for the evolution of the major remnant. Left figure shows the with viscosity and the right figure shows the with no viscosity. So let's try again. In the absence of the viscosity, where non-axisymmetric structure is preserved and some angular momentum transport occurs, and then so spiral arms continuously generated. But in the presence of viscosity, initially we have angular momentum transport, but after 5 milliseconds, angular momentum transport stop. And you can see that fairly spherical, spheroidal remnant after the angular momentum transport. The reason is that quite simple. So in the presence of viscosity, initially differential rotating profile changed to the rigidly rotating profile like this. This is a red line shows the initial profile, and the pink line shows the profile at about 20 milliseconds. So anyway, so in the presence of viscosity, angular momentum transported, and then eventually rigid rotation is satisfied. And with this phase, so non-axisymmetric degree of the remnant massive neutron star essentially disappear. And this is a gravitational waveform in the presence of viscosity for red, and in the absence of viscosity with red, and in the presence of the viscosity for green and blue. In the absence of viscosity, due to the quasi-periodic nature, gravitational wave emission continues for a long time. For long time means more than 20 milliseconds. But in the presence of viscosity, this gravitational wave dumps soon, like this. So that means that depending on the turbulence is excited or not, so strength of gravitational waves is highly different. Okay, so this is summary. So in astrophysics and in neutron-star merger, effective viscosity often plays an important role, and it comes from the magnetic hydrodynamics instability. And in the presence of such an effective viscosity, remnant of neutron-star merger are very, very subject to the effect of effective viscosity. And the remnant disk obviously is affected significantly by the effective viscosity. But on the other hand, for remnant neutron star, we don't know what happens because we don't know whether turbulence is excited or not. But as I showed, in the presence of the turbulence, then so effect is significant. For example, post-merger gravitation waves, amplitude of post-merger gravitation waves are highly affected by the turbulence viscosity. And post-merger gravitation waves attract attention from the gravitational community and the nuclear physics community. But to understand the details, we need to understand the turbulence in detail. Okay, thank you very much. I think just on time.
Thank you for staying on time. And indeed, there are already some questions in the chat. So I think I'll start asking these people to say their question out loud, and otherwise you can also raise your hand or keep on typing. So Igor, maybe you can start since you're the first.
I was wondering about the different mechanisms for the viscosity due to the electron capture and neutron decay in neutron stars. Usually that is considered to be one of the dominant mechanisms for the bulk viscosity. Why you don't consider that? It should be also millisecond timescale.
Well, so as I said, so we're naively thinking that we need a very good choice of the mean free path. How can you achieve such a mean free path?
Well, here it's not the mean free path of neutrinos exactly. It's actually simply a dynamical viscosity due to the fact that neutrons will be decaying into protons, and protons will go through the electron capture into neutrinos. So back and forth, it should give an effective dynamical viscosity.
Yeah, but then so how large is the mean free path? So
well,
anyway, viscous coefficient is roughly speaking by the order of magnitude. So sound velocity multiplies the mean free path. So yeah, then what is different? So
the difference is that this is actually kind of like zero frequency, or if you wish, it's like omega to zero limit of the viscosity. The dynamical viscosity happens due to the dynamical scales set up by the processes in the star. So essentially compressions, decompressions. So it's essentially macroscopic time scales, and therefore the corresponding dynamical viscosity should be small. Sorry, small, on the time scales of milliseconds.
So you mean that so formulation for viscous coefficient is different in your scenario, right?
Yes. Yes.
Okay, so then yeah, if we such a mechanism exists, so yeah, then so it could give an effect. That's right. Anyway, so but in the very naive estimation, so this I think that you agree with this. But,
yeah. No, this is fine.
Yeah. But in the presence of some other effects, so maybe But
Okay,
no one knows inside the Neutron-star.
Quite some more questions. Maybe I think Urs was second.
Yeah, Shibata, thank you very much for this interesting talk. This is Urs Wiedemann from CERN. So effective viscosity is viscosity that comes essentially from you do a hydro simulation in some region of phase space over some range of wavelengths. But there is always another region of wavelength into which energy can dissipate where it is lost, where it's not followed dynamically in your simulation. This turbulent viscosity is one particular way of doing thinking about effective viscosity, and it's the most abundant one. But there can be other sources, for instance, in large-scale structure simulations, even in the weakly nonlinear regime, one knows that the coupling to excitations of smaller wavelengths introduces some effective viscosity. So my question is twofold. On the one hand, do you know whether that is really the turbulence that is the dominant spectrum to which you have to couple? Or could it be some other small scale feature to which you need to couple your hydrodynamics, and that is accounted for by viscosity? That's the first point. And the second question is, in practice, all these effective viscosities amount to write in viscosity as an integral over a spectrum in the region that is not simulated. So whatever you assume about the size, it depends on what you assume, in your case, about the eddy structure. So how can you hope to become quantitative here? You said you make a simulation with some ansatz, this alpha equals 0.01 or so. But in the end, as long as you don't know the spectrum of your eddies.
Yeah, you're right, completely right.
What can you do?
You completely right. So as I said, but it's impossible to do right now. So yeah, also for...
Well, I mean, in large-scale structure, for instance, people have n-body simulations from which they take the spectrum. So you have something similar.
Much more expensive. Do you understand?
Yeah, that I understand, of course.
Much more expensive. You're completely right. I would like to do, but it's quite expensive. Please prepare for me the huge computer. Then we can do.
Okay.
This is the answer.
Okay, that's a clear question, clear answer. George, after this, I think.
Yes. Hi. Thanks for this talk. It's just a quick question. When this turbulent viscosity, so in your paper, this contributes to bulk and shear viscosity at the same time, and I'm not sure if this is because of this very simple formulation of Israel that you had, but is this supposed to be a mechanism that generates shear, bulk, and thermal connectivity, or just one of them?
Well, so it's a very primitive simulation. So yeah, so this is I think that this is the first GR simulation with viscosity. Yeah. Then so at that time we just consider that so in the first step that's fine. So of course it's better to take into account the bulk viscosity, but in the presence of bulk viscosity numerical level, so we need an additional idea. Because
I think the question was not that. The question was like, if you expect that all of them would show up. I understand that it's hard to do even one, but do you expect that this mechanism would create different channels like shear, bulk, and thermal connectivity? Okay.
Yes, it's possible to do, but we need another numerics.
Okay, thank you.
And then there's a raised hand by Travis.
Hi, I just had a particular question about what do you mean when you say the simplest version of Israel's Stewart, and how do I see where the effective viscosity enters into to the equation?
So I only consider the evolution of the viscous tensor. So we omit everything, every other effect. So because in the original version of the Israel Stewart formalism, so there are many so thermal conduction and so on. But so we neglected all other things, just take into account shear viscosity.
And so how do I see where the effective viscosity enters into the equations? So when you say do you have a relaxation time for the
Yes. Yeah. Also, well, so everything is very phenomenological, and the relaxation time is usually should be so microscopic level. But here I choose a very small number, but it's still very large.
Because for once, like you have a lot of you talk about all these eddies and vorticity and everything, and when I think of when I think of the simplest version of visual Stewart, if you're saying you just have shear viscosity in it, right?
Yeah, viscosity.
Stewart, there should be coupling.
And the coefficient is time scale is very long compared with the molecular viscous time scale. Unfortunately, it's impossible to do for simulation for molecular viscous time scale.
Maybe also raised hand by Elias Moss.
Or Elias.
Oh, hey, Masaru.
Yeah.
I wanted to ask about your global simulations with viscosity, where you basically put, that's a uniform number that you put, right? I was just wondering, like, what did you ever try out, like putting like a different viscosity in the disk and a different viscosity in the star? Because in principle, while in the disk we have some feeling, right? I mean, in the hypermassive neutron-star, if you have magnetic braking, that would have like a different different scale.
Maybe it's better to show. Yeah. No. 消えてしまった。Well, so we did. So please take a look at the paper by Fujibashi et al. So this year, so we performed a simulation for which viscosity is on in the disk, but off in the neutron. But even in this case, the result doesn't change so much. But for neutron-star, so effect of viscosity is significant. But for disk, so even if maybe so it's not very easy to say right now. But
so what you're basically saying is that not having viscosity in the neutron star doesn't change like the interface between the disk and the star. So there's no
and also doesn't change mass ejection significantly.
Interesting.
Yeah.
Okay, so one more minute. So maybe one last question by Ho.
Hi. Could you explain how eddies amplify magnetic field? I understood that the matter we are considering is neutral.
No. So it's always a magnetic field present in the presence of an electron, and Anyway, so usually we believe that magnetic field in the neutron star is produced by the motion of the electron, and then so electron motion. So we have the magnetic field structure, and but in the presence of this kind of eddy, so magnetic field is wounded. Then so magnetic flux here is increased, and then for example, initially we have only one magnetic loop, but in the presence of windings, we have a huge magnetic flux in this radius. Then so magnetic field is amplified. Yeah, just winding.
Thank you. Yeah. Bye.
Yeah.
Thank you.
I think then there's still a little bit of discussion in the chat by Gabriel and Thomas Schaefer about turbulent viscosity. I mean, maybe you can reply on the chat, or if anybody wants to ask that out loud, that's also possible. Otherwise, I think we thank Shibata again, and we go to the next slide. Luis, if you can share your